Okay, so this evening we are going to talk about something called the work energy theorem. And this work energy theorem is also called the principle of work and kinetic energy. So the work energy theorem gives us a connection between work done and the kinetic energy. Now, where does this principle work? The principle of work and kinetic energy, where and how do you use it? Okay. Now, for you to use this principle, of course, you need to have a mass m where work is done. So you need to have an object on which you need to do work. So once this work is done on this particular object, and the other requirement is that there is no change in gravitational potential energy. So we know that gravitational potential energy is the energy an object has as a result of its height above the surface of the earth. So what we are saying is that the gravitational potential energy should not change, or the height of the object should not change, it should stay the same. So if you do work on an object, meaning that you're going to transfer energy to this particular object, and in the process of doing this work, as you are doing this work, the height of the object or the gravitational potential energy of the object does not change, then the work you have done is going to appear as kinetic energy. So the energy transferred to the object, because when you do work, you transfer energy to this particular object. So the energy you transfer to the object can only appear as kinetic energy. So when you perform work on an object, there is going to be transfer of energy from you who is doing the work to the object you are doing work on. As long as there is no change in height, meaning that the gravitational potential energy remains the same, then that energy you have transferred to this particular object will appear only as kinetic energy. So this particular object will have to move. So what we are saying is here that the work done is equal to the change in kinetic energy as long as the gravitational potential energy remains the same. So the height of this particular object, or basically the height, doesn't change. So that is the statement of the work energy theorem. So I'll repeat again. When you do work on an object of mass m, as you are doing this work, and the height of this object does not change, it remains the same, meaning that there is no change in gravitational potential energy, then the energy you transfer to the object as a result of you doing work can only appear as kinetic energy. So the work done is equals to the work you're going to do, the size of the work you're going to do is equals to the change in kinetic energy which that particular object is going to undergo. So work done is equals to the change in kinetic energy. The delta here represents a change in kinetic energy. Whenever you have got change in a physical quantity, then we are talking about having a final kinetic energy, which is KEF, and having an initial kinetic energy, which is KEI. So your final kinetic energy minus your initial kinetic energy, that is what is going to give you the change in kinetic energy. So when you do work on an object, the kinetic energy of that particular object has to change. How do we know that the kinetic energy has to change? It's because as the object moves, it also covers some distance. For you to do work, the object has to change its position from this particular point to that particular point. So there has to be some distance this particular object is going to move. So the final kinetic energy, KEF, is equals to half multiplied by the mass multiplied by V squared. V squared is the final kinetic energy. V is the final kinetic energy. So if V is the final kinetic energy, you want half times the mass times V squared. This gives you the final kinetic energy. Then this one, KEI, is equals to half the mass times U squared. This is the initial kinetic energy. So we have the initial kinetic energy there. So, yeah. So if there is a change in kinetic energy of an object, then this change in kinetic energy is equals to the work that is going to be done, and this is how you write it. So you can write the whole thing and one thing. The change in kinetic energy is equals to half mv squared, half mv squared minus half mu squared, where the v is the final kinetic energy, the u is the v is the final velocity of the object, the u is the initial velocity of the object. If, of course, the final kinetic energy is greater than the initial kinetic energy, then the change in kinetic energy is going to be positive. This change in kinetic energy, if it's positive, it means that energy was added to this particular object. If the change in kinetic energy turns out to be positive, it means that this particular object received energy. That means that the work done was positive. The work done resulted in a transfer of energy from the object which was performing the work to this particular object on which the work was done. Here's an example. Of course, again, you can have change in kinetic energy which is equals to negative. So if the change in kinetic energy is negative, it means that the final velocity is less than the initial velocity. So in that case, if the change in kinetic energy is negative, it means that this particular object lost energy. And the way objects lose energy is if you have a force like friction performing negative work. So the force like friction is going to point in the opposite direction, and the object is going to slide the other direction. So the angle between the friction force and the direction in which the object is going to be 180 degrees. So in such a case, we have seen that the work which is going to be done will be negative. If negative work is done, that negative work results in energy being removed from the object. Here we have an example. A 0.5 kg block slides across a table with an initial velocity of 0.2 meters per second and comes to rest at a distance of 0.7 meters. Find the average frictional force that retards its motion. So we know the mass of the objects, it's 0.5 kg, and when this particular object started sliding on a table, across a table. So if you have a table is flat. So on a table, the object does not experience a change in height. The height of the object above the ground stays the same. So if something is sliding on a table, there will be no change in gravitational potential energy. So one of the requirements of applying the work energy theorem is that the gravitational potential energy should not change. And a table meets this requirement. Any sensible table meets the requirement of being flat. So as our particular object is sliding with initial velocity 0.2 meters per second squared, this is the initial velocity, and we are told it comes to rest. When it comes to rest, its final velocity is going to be equal to 0 meters per second squared, and during this time it covers a distance of 0.7 meters. So this particular object, its final velocity is 0, its initial velocity is 0.2 meters per second squared. So we can work out the initial kinetic energy of this particular object and also the final kinetic energy of this particular object. The initial kinetic energy, KEI, is going to be equal to half multiplied by m multiplied by u squared. The m is the 0.5, which we have here, and the u is the 0.2 meters per second squared, which you have there. So that's going to be half 0.5 kg times 0.2 meters per second, 0.2 meters per second. The whole thing squared, that is going to give us 0.01 joules. Since the object comes to rest, its final velocity is v with 0. So our final velocity v is equal to 0 meters per second. So we can work out the final kinetic energy, KEF, which is going to be half, then the mass of the object times v squared. So in this case, your v is your 0 meters per second because the object comes to rest. So we end up equal, this is going to be equal to half, then 0.5 times 0 meters per second squared, which is going to give us the 0 multiplied by everything else is going to give us 0 joules. So we have a initial kinetic energy of 0.01 joules. You've got a final kinetic energy of 0 joules here. The change in kinetic energy is going to be equal to the final kinetic energy minus the initial kinetic energy. In this case, the final is 0 joules minus the initial, which is 0.01 joules, which is going to give us a change in kinetic energy of minus 0.01 joules. So the change in kinetic energy, as you can see here, is negative. This negative means that during the process of this particular object sliding to a stop, it lost kinetic energy. And the reason why it lost kinetic energy is because the kinetic energy it had was taken away from it. And the reason why it was taken away from it is because negative work was being done by friction. If something is sliding to a stop, the reason why it's sliding to a stop is because there is friction at work. Okay. Now, for us to use the work energy theorem, in this case, a requirement has to be met. The surface on which this particular object is sliding has to be flat, and the table meets that requirement. Across a table, if something slides on a table, there is no change in gravitational potential energy. So the gravitational potential energy is the same. So the gravitational potential energy is the change in gravitational potential energy is equal to 0. Yes, there's a question? Is there a question? Okay. So if the change in gravitational potential energy is equal to 0, then we can use the work energy theorem. What does it tell us? It tells us that the work done is equal to the change in gravitational potential energy, in kinetic energy. The change in kinetic energy, we have it, is this one here. So the work done is going to be also going to be negative. It's going to be minus 0.01 joules. Now, the force which does work in this case, in bringing this particular object to a stop, is the friction force. And the friction force always acts in a direction opposite the displacement. So the angle between the friction force and the displacement s, which is equal to 0.7 meters, is 180 degrees. So in that case, we can work out the work done by friction. Work done is going to be because the friction force multiplied by the displacement multiplied by the cosine of the angle between the friction force and the displacement, which is equal to 180 degrees. So the work done is going to be because the friction force multiplied by 0.7 meters multiplied by the cosine of 180 degrees. And this cosine of 180 degrees is going to give you a negative 1. So we equate this bit, which is the work done, to this bit, which is the change in kinetic energy. So when we equate them, this is what we end up with. And this bit is negative 1, so you end up with a negative here, negative friction force multiplied by 0.7 meters, 0.7 meters equals to minus 0.01 joules. You divide by minus 0.7 meters on both sides, so you end up having the friction force being equals to minus 0.01 joules divided by minus 0.7 meters, and this gives you a friction force of 0.014 newtons. So in this case, the friction force which is responsible for bringing this particular object to a stop is equals to 0.014 newtons. One of the things you see about friction is that usually friction, the force of friction is very small. But this force of friction is still enough to bring an object to a stop. Even if friction is small, but it will eventually bring whatever particular object you have sliding on your table or on the floor, that particular object will eventually come to a stop. Is it clear on how we use the work energy theorem? There is a requirement which needs to be met. The change in gravitational potential energy has to be equal to 0. So there should be no change in the height of the object for you to use the work energy theorem. Are we clear? Any questions? Next example, example 7. The coefficient of kinetic friction between a 900 kg car and the pavement is 0.8. a quite high coefficient. If a car is moving at 25 meters per second along the pavement, along the level pavement, when it begins to skid to a stop, how far will it go before stopping? So again, this question is just basically the opposite of what you're doing here. So we have a car with a mass of 900 kg. The coefficient of friction, we are told, is 0.8. So you know that there's friction at work here. Friction is the one which is going to bring this car to a stop. The velocity of the car, initial velocity of the car is 25 meters per second. And of course, we are told the car skids to a stop, which means that it's going to have a final velocity of 0. So the velocity of the car changes from 25 meters per second to a velocity which is equal to 0. We are also told that the pavement is level. So this level pavement, it's a flat pavement, means that the pavement's height is not changing. So there is no change in the gravitational potential energy of the car as it is skidding on this pavement. With this requirement met, that the change in gravitational potential energy be equals to 0, and since the kinetic energy of the car is changing, we can use the work energy theorem. So we proceed to work out how much the change in kinetic energy is going to be. So the change in kinetic energy is going to be equal to half mv squared minus half mu squared. In our case, since the car comes to a stop, skids to a stop, so our v is equal to 0 meters per second squared. The initial velocity of the car is 25 meters per second squared there, and we know the mass of the car is 900. So we can work out how much the change in kinetic energy is going to be. That's going to be half mv squared minus half mu squared. If you substitute, it's going to be half 900 kg multiplied by 0 meters per second, the whole thing squared, minus half 900 kg, then 25 meters per second, the whole thing squared. And the change in kinetic energy is going to be equal to minus 281,250 joules. So this is going to be your change in kinetic energy. So as you can see, for a car which weighs 900 kgs, when this car comes to a stop, it loses a huge amount of energy. So with this bit met, we are being asked to find how far the car is going to go. Basically, we are being asked to find the stopping distance. So for us to do that, we need to find out how much the friction is. So in this case, we know that the coefficient of friction is 0.8. So using the coefficient of friction, we can work out the friction. Friction is going to be equal to the coefficient of friction multiplied by the normal force. Since we are on a level of ground, we know that the normal force, Fn, is equal to the mass of the car multiplied by the acceleration due to gravity, or basically the weight of the car, which is, so Fn is equal to mg. So the friction force is going to be equal to the coefficient of friction, mu k, multiplied by mg. So the friction force is going to be equal to, in this case, 0.8 multiplied by 900 times 9.8 meters per second squared, and you get a friction force which is equal to 7,056 newtons. This is how much the friction force is going to be. With this amount of friction force, we also know that friction always acts in a direction which is opposite the direction of motion. So this one, we know this bit about friction. So the angle between the friction force and the displacement, which we are looking for, or the stopping distance, is going to be equal to 180 degrees. So the work done is going to be equal to the friction force multiplied by the displacement multiplied by the cosine of the angle. So the friction in this case is 7,056 newtons multiplied by the displacement s, then multiplied by this bit, which is going to be a -1. So we end up having work done being equal to minus 7,056 newtons multiplied by s, which is the displacement. Since the pavement is level, so we can use, this whole thing is happening on a level pavement, then we can apply the work energy theorem, which says that on a level pavement, the change in kinetic energy is equals to the work done, and we have both of these things. This is the work done. We also have the change in kinetic energy. So we kept them. So the work done is this bit minus 7,056 newtons times s, which is the displacement, being equals to minus 281, then 250 joules, like that. So if you divide both sides, you end up having your S, which is the displacement, being equals to minus 281,250 joules divided by minus 7,056 newtons, and this is going to give you a displacement which is approximately equals to 40 meters. So basically your car, or whatever this car is, comes to a stop in 40 meters. Are we clear on how we use the work energy theorem? There is a requirement which has to be met. The change in gravitational potential energy has to be equals to 0. So the height does not need to change. So if the height is not changing, then the work done is going to appear as kinetic energy. Then next we come to the principle of conservation of energy. Now in the principle of conservation of energy, the change in gravitational potential energy is not equal to 0. So in this case, we are allowing the height of the object to change. Now, the principle of kinetic conservation of energy basically says that with these forms of energy you're interested in, mainly kinetic energy and gravitational potential energy, what it says is that the sum, when you add the change in kinetic energy of an object, and you also add the change in gravitational potential energy of an object, these should always be the same. They should be constant. And this constant is basically 0 here. So when an object experiences a change in kinetic energy, so you find out how much the change is, then you add this change in kinetic energy to the change in gravitational potential energy. Then you should end up with a constant, and that's what's supposed to be 0. How I would explain this is that, for example, if you have a car, you were driving a car or something, then this particular something goes uphill. When that particular object is going uphill, it is gaining gravitational potential energy. However, as it is going uphill, it is losing kinetic energy. So you can't have both at the same time. Either you are gaining kinetic energy, but as you are gaining kinetic energy, you are losing gravitational potential energy. So that when you gain kinetic energy and when you lose gravitational potential energy, at the end of the day, when you add them, what you end up with is 0. Or you are losing kinetic energy, but you are gaining gravitational potential energy, so that at the end of the day, we end up with a 0. So that's what the principle of conservation of energy says. Are we clear? With the principle of conservation of kinetic energy, there is a change in the height of the object. So as you go up, climbing up, you are going to become slower. A good example is when you throw something upwards. As you throw a stone upwards, that particular stone is gaining gravitational potential energy, but it is becoming slower. So it is losing kinetic energy, and eventually this particular object you have thrown up is going to reach what we refer to as maximum height, which is the height at which an object has got a velocity of 0. So when it reaches maximum height, it would have gained the maximum gravitational potential energy, but it would have lost the kinetic energy it had. If you add up the gain in gravitational potential energy and you add up the loss in kinetic energy, you end up having a 0. Here's an example to demonstrate that fact. Here, a 1 kg projectile is shot upwards from Earth with a speed of 20 meters per second. How high is it when the speed is 8 meters per second? So in this case, some projectile is being shot upwards with a velocity of 20 meters per second, and of course, as something goes up, its velocity has to reduce. So eventually the velocity of this particular object reduces to 8 meters per second. So if the velocity was 20 meters per second initially, then the final velocity at some height is 8 meters per second. So you can see that this particular object has lost kinetic energy. So the change in kinetic energy is going to be equal to half multiplied by the mass multiplied with the final velocity squared minus half the mass, the initial velocity squared. The initial velocity u is 20 meters per second. The final velocity v is 8 meters per second. So when you make your substitutions, the change in kinetic energy is going to be equal to half times 1 kg times 8 meters per second squared minus half 1 kg times 20 meters per second squared. And in this case, your change in kinetic energy is going to be equal to minus 168 joules. This minus is telling you that this particular object lost kinetic energy in the process of getting up to whatever height this was. So the minus is telling you that the object lost kinetic energy. However, something else also happened. As this whole thing was happening, this particular object gained height. If the object gains height, it means that there is a change in gravitational potential energy because the object has gained a particular height. So what we are told according to the conservation principle of conservation of energy is that the change in gravitational potential energy plus the change in kinetic energy is going to be equal to 0. This is the constant we are talking about. If there is a loss in kinetic energy, there has to be a gain in kinetic energy. The size of the loss has to be equal to the size of the gain of the gravitational potential energy, such that when you add up these quantities, you end up with a 0, like that side. So in this case, the change in gravitational potential energy plus the kinetic energy change is negative, meaning that the kinetic energy was lost. So you put it as negative 168 joules is equals to 0. So this gives you the change in gravitational potential energy equals to minus 168 joules equals to 0. So at the end of the day, you end up with this. The change in gravitational potential energy is equals to 168 joules. That's how much the change is. The change in gravitational potential energy is equals to 168 joules. Okay. Now, the change in gravitational potential energy is given by this. The mass of the object multiplied by the acceleration due to gravity multiplied by the height through which this particular object went. So in this case, if we work out this, we know that the mass of the object is 1 kg times g, which is 9.8 times the height. This gives us an expression for the change in gravitational potential energy, which we know is equals to this. So when you equate them here, this is what you end up having. The change in gravitational potential energy is equals to also this 168. So you can make h the subject of the formula by dividing through by this 1 kg times 9.8 on both sides. So you end up having a height h is equals to 168 joules divided by 1 kg and 9.8 meters per second squared. So you get a height of 17.1 meters. So our projectile is going to rise to a height of 17.1 meters. So this is us putting in practice this thing which is called the conservation of energy. In a nutshell, the conservation of energy just says that you can't create or destroy energy. Okay? You can't create or destroy energy, but the only thing you can do is convert energy from one form to another. The conversion of energy from one form to another is allowed to happen. Okay? However, you cannot destroy energy. This thing also works when the change in gravitational potential energy is equals to 0. So if you're on a flat table, and if you're on a flat table, of course, this bit, delta, the change in gravitational potential energy is going to be equal to 0. So you're only going to remain with this, the change in kinetic energy. Now, when something slides on a table, clearly that particular something is losing its kinetic energy. So does the kinetic energy of an object sliding on a table just disappear like that? No, it's not allowed to disappear like that, but the kinetic energy is converted into another form of energy. In this case, since the table is flat, it cannot be converted into gravitational potential energy, but it is converted into what is known as heat. Heat is a form of energy called thermal energy. So in this case, if you have an object sliding to a stop, if an object slides to a stop, that particular object loses its energy. That energy does not just disappear like that. That energy is converted into heat, which is emitted into the environment. So there is really no making energy disappear just like that, or destroying energy or creating new energy. No. You can capture one form of energy, then you can convert it to another. That is allowed. Are we clear?
Yes, sir.
Okay. The next bit which we need to look at is something called power. Now, power refers to how fast you're doing work. And you have to remember what you're doing when you're performing work. When you perform work, you are transferring energy to the object you're doing work on. Okay? When you perform work, you are transferring energy. It depends on what kind of work you're doing. If the work you're doing is positive, meaning that you are transferring energy to this particular object, if the work you're doing is negative, it means that you are taking away energy from this particular object. So when we're talking about power, basically we are finding out how fast are you doing work. So you do a certain amount of work, then the amount of work you've done, we divide it by the amount of time it took you to do that particular work. And that's what is referred to as average power. So average power is the work done by force divided by the time taken to do the said work. So in this case, the power is P, work is W, and the time is T. We know from our definition of work that work is equal to some force. So you need some force for it to do work. Then this particular force should cause an object to move through some distance S. And of course, there might be some angle between this particular force and the displacement. Then this whole thing, Fs cos theta divided by T. To make things simple for ourselves, we look at a case where the force you are applying on this particular object and the displacement in which this particular object moves are in the same direction. So the force and the displacement, if they're in the same direction, then in that case, your theta is equals to 0 degrees. So in this case, the force, which is a vector, and the displacement, which is also a vector, are pointing in the same direction. If they're pointing in the same direction, then this theta is going to be equals to 0 degrees. And cos theta is just equals to 1. So we end up having power being equals to the force multiplied by the displacement divided by the time. With this expression, that if you factor out the F, you end up having S, which is the displacement divided by the time. This S is the distance in a specific direction, in a straight line, which the particular object moves. So the object has to cover some distance. Then you divide this distance by the amount of time it takes to cover this distance. Then you end up with what you call average velocity V. So you can also define power in this case. This is a very special case when you're using this expression of power. Power equals to the force you have applied times the average velocity. So in this case, you can define power if the force and the displacement are in the same direction, then the power can be defined as equals to the force multiplied by the average velocity. They're in the same direction. Of course, if the force is going to be in the opposite direction, like in the case of friction, friction is not going to do power, positive power. It's going to remove energy. So basically, your power is going to be negative. So we basically specifically look at the case where the force and the displacement are in the same direction. So you end up with this expression of power where this is your force, and this V is not your final velocity, but this V is your average velocity, because you divided the displacement, the total displacement covered by an object, divided by the time it took. So that gives you the average velocity. So you end up having this thing for power. So you can work out the power in terms of the work done, how fast work is being done, the work done divided by the time. So that's the rate of doing work. Or you can multiply the force, a product of the force, times the average velocity of the object, like that. So that would give you a power. The units for power, the SI units, is the watts. And in the case of 1 watt, the symbol is W. 1 watt is defined as you performing work, which is equals to 1 joule of work in 1 second. So 1 joule of work in 1 second is going to result in the transfer of 1 joule of energy per second. That's what's going to happen. Another way is if you look at it in terms of what you have this side. So if you've got a force of 1 Newton, then this force of 1 Newton acts on an object, and that particular object moves with an average velocity of 1 meters per second. So if you've got a force of 1 Newton, it acts on an object, and the object in question moves with an average velocity of 1 meters per second, then the power in that case is 1 watt. A useful unit of power is what is called the kilowatt hour. Now, the kilowatt is basically 1,000 watts. And hour is, of course, a unit of time, 1 hour. So what you are doing here, if you want to use the kilowatt hour, what does it actually mean? The kilowatt is for power, the P, this side, here. So you have power, which is measured in kilowatts, 1,000 watts. Then you've got time, which is the hour, which is measured in hours, which is this T. So you have multiplied this power times the time. So if you multiply the power times the time, what you actually end up with is work. So this kilowatt hour is basically actually a measure of work. If you transfer, as you are doing your work, you do your work, then you transfer 1,000 watts of power, which is what is called 1 kilowatt. Then this 1,000 watts of power, you transfer it over a period of 1 hour. Then how much work have you done? So in that case, that's what we're trying to do here. So 1 kilowatt hour, so this, the equivalent of this is basically the kilowatt is, the kilo is 1,000, then the watt is just a joule per second multiplied by the hour, 1 hour, which is there. Then an hour has got 3,600 seconds. So this 1,000 joules per second times 3,000 seconds, like that. So the seconds, this and that, they cancel out. So you end up having 1 kilowatt hour being equals to 3,600,000 joules of energy. So in 1 kilowatt hour, you are going to perform work which is going to result in the transfer of 3,600,000 joules of energy. So this is a large unit. This is a large unit of work or power. Since we know now we are measuring things in hours and how much power, how much work, or how much power has been done in that same amount of time. Okay. Any question?
I have a question, sir.
Yes.
Earlier you mentioned that energy is neither created nor destroyed.
Yes.
Now, where is energy coming from, actually?
The energy we use on the planet comes from the sun. All the energy we use on Earth comes from the sun. Without the sun, we will be short of energy and life will not be possible. Because of the sun, some of that energy is used for example, it heats up oceans. Then these oceans became turbulent. So there is wind generated. From that wind, you can create, there is all these things called wind turbines. From the wind turbines, you can generate electricity. Also from the waves, there's something called tidal tidal things, when waves are moving, water is wave stuff, you can use waves to generate electricity, but some of the other energy is captured by plants and trees. And when these plants and trees, they rot or they are buried, like they have been done for many years, millions of years, then you end up having something called petroleum, which from where we get petrol and diesel, and also kerosene, and you also get something called natural gas, and also something called coal. So this whole thing is because these plants captured energy from the sun. Also, when you eat food, the food you're eating, most likely there's a plant somewhere involved, a plant which captured energy from the sun using photosynthesis. Then that plant was eaten by a cow or a goat which produced beef. In that beef you're eating, that meat, there's energy also. So the energy, the solar energy from the sun, is captured in one form or another. And as you can see these days, now we try to do the same photosynthesis but artificially using solar panels. So we try to capture the energy from the sun, then we change it into another form of energy, which is chemical energy, electric a bit, first electric, then we store it in batteries as chemical energy. Then once you have it stored in batteries, you can use it again in whatever form of energy you want. So the sun itself makes this energy, or I can say makes this energy using a process called nuclear fusion, where it combines hydrogen atoms together to form helium atoms and other bigger atoms, and in the process of doing that, it emits a lot of energy. So basically, on Earth, if you want to create energy per se, create, you have to do what is called nuclear reactions. Any question?
No question.
Okay. All right. This example is not supposed to be, it's supposed to be somewhere up there. So the example probably you would look at is this one here. Calculate the average power required to raise a 150 kg drum to a height of 20 meters in a time of 60 seconds. So when you are raising things, when you are lifting something up to a height of 20 meters, there is a change in height. Since there is a change in height, then this particular drum is gaining energy in the form of gravitational potential energy. How did the drum gain the energy? The only way a drum is going to gain energy is if you have done work on the drum. So the act of you lifting, when you are lifting something from the ground to a particular height, you are doing work. Okay? So when you're lifting something, you're doing work. Now in this case, we are assuming that as you are doing this work and lifting this work, you're doing all this at constant velocity. Basically, that's our assumption here. We assume that all this thing is happening at constant velocity. So if it's happening at constant velocity, then it means that there is no acceleration. If there is no acceleration, it means that your lift force should be equal to the weight. So you are lifting something up, you're pulling something up, and that particular something is coming along with you up. So your lift force is pointing up, then the height through which this particular object goes through is up. So the lift force and the height, or the distance the particular object travels, are in the same direction. But all this is happening at constant velocity. So if there is no acceleration, then your lift force is equal to the weight of the drum. So the weight of the drum, Fw, is equal to the mass of the drum times acceleration due to gravity. So the mass of the drum is 150 kgs. Then the acceleration due to gravity is that. So we end up having a weight which is equal to 1,470 newtons. Because we are assuming that there is no acceleration, so the lift force, the force pulling the drum up, and the weight of the drum, they should be equal. So in this case, you end up having your lift force F, being equal to the weight of the drum, which is equal to 1,470 470 newtons. So we have the force. The height through which the drum is lifted is the displacement, and it is the same direction as the lift force, and that is 20 meters. So in this case, the angle between the lift force, the direction of the lift force, and the direction of the displacement is going to be equal to 0. So you can work out the work done. Work done is going to be equal to the lift force multiplied by the displacement, or the height through which the drum is lifted, times the cosine of the angle between the lift force and the displacement through which the drum is lifted, which in this case is going to be equal to 0. So you end up having the work done as 1,470 newtons times 20 meters times the cosine of 0 degrees, like that. So this whole bit gives you work done being equals to 29,400 joules. So this is work. This work done, as you can see, is positive work. So you are doing positive work. Now, as you are doing this positive work, your drum is gaining this energy, 29,400 joules, in the form of gravitational potential energy, because the height of the drum changes. So basically, this is the work you've done. And we are told you have to do this over a period of 60 seconds. So if the work we have done is 29,400 joules, then the power is going to be equal to the work done divided by the time, which is 60 seconds. So the average power is going to be 29,400 joules divided by 6 seconds, and that gives us a power of 490 watts. So basically, per second, the drum is gaining, each second which passes by, the drum is gaining 490 joules of energy per second. Then over a period of 60 seconds, it gains 29,400 joules of energy, which is its gravitational potential energy in this case also. Are we clear?
Yes.
Any questions?
Yes.
If there are no questions, we'll come to a stop here. Huh?
Sir.
Yes.
Sir.
Yes.
I have a complaint on your system.
You have a complaint?
On the past, yes, on the past quiz.
On my past quiz?
One question I was told, yes. One question I was told is correct. After it marked me wrong, but I looked on the other account for my friend. The same question which said was correct. That's wrong again.
Those are computers, my friend. That has got nothing to do with me. You have to, if you have got a genuine complaint, you have to go and see Mr. Chimba in the physics department, so that he takes note of what question that was, so we can see which question has a problem. Then maybe you can make some changes. But otherwise, it's not really me. Okay? So go and see Mr. Chimba on Monday.
All right.
Yes. Any other questions? Okay, so if there are no other questions, we come to a stop here. Of course, this thing was being recorded, so we're going to post the recorded video on YouTube and also share the link in your Moodle. Okay.